Welcome everyone to our webinar titled New Efficiencies in Area Mapping, Performance and Planning with Regal's VQ1560 Mark IIs and TopalFlight Mission Planner. My name is Michael Sitar and I am a division manager for the ALS scanning products here at Regal USA. Today I have the distinct pleasure of doing a joint webinar with Klaus Budmiger, CEO of TopalFlight Systems. TopalFlight is a flight management software and hardware system for the effective mission planning and navigation of various remote sensing systems, including both LiDAR and imaging sensors. Founded in 2003, Klaus has been the principal programmer for TopalFlight Systems, focused on software development and systems integrations, and also serves as a consultant for various aerial survey companies. Currently living in Switzerland, Klaus began his career studying surveying, geodesy, and photogrammetry at Basel Institute of Technology in New South Wales University in Sydney, Australia. After graduating, he did a postgrad in software engineering. And in addition to the development of TopalFlight, Klaus has spent 20 years teaching photogrammetry as a part-time professor at the Institute of Geography at University of Bern in Switzerland. And he also works as a consultant since 2015 as head of photogrammetry of Flowtron, Switzerland. Klaus, welcome.
Hi, glad to be here. Thank you.
Today we'll have a brief look at Regal's latest release of its popular VQ1560 wide area LiDAR mapping sensor, the Mark IIs. The Mark IIs features a new multi-laser subsystem that further raises the bar in collection efficiency and productivity. This webinar will also demonstrate collection efficiencies possible with the 1560 2S using the TopalFlight flight management system, a recent addition to Regal's available flight mission management choices. This will consist of a live demonstration of the TopalFlight Mission Planner software to provide you with an overview of the principal workflow and available mission evaluation data products. The Regal Airborne product line consists of numerous sensor choices depending on application needs. For wide area mapping applications where longer range performance is required to address both topographic variation and increasing area collection needs, we recommend the VQ580, the VQ780, and the VQ1560 Mark II and 2S sensors. The VQ1560 2S is at the top of the heap where statewide area collections are desired with maximum collection efficiency. Not apparent in this chart is the predecessor to the Mark IIs, the Mark II. We will continue to offer the Mark II for those surveyors whose application requirements do not demand the range performance that otherwise comes with the Mark IIs, but can benefit from the unique performance and configuration advantages that the 1560 sensor platform offers. The VQ1560 2S is really a hybrid LiDAR and imaging solution consisting of a dual laser system in combination with a dual camera system fully embedded in the same sensor housing. The sensor's inherent feature sets and scan geometry have been carefully selected to optimize target coverages and point distribution to provide 2D and 3D output products that can be rapidly converted to actionable data. Improvements in beam divergence translate to increased target resolution, and an extremely fast scan rate ensures full use of the variable PER to be equally distributed over the ground, even at low altitudes and faster platform speeds. The whole sensor is configured, controlled, and monitored using an onboard acquisition system that centralizes sensor configuration, control, and monitoring. The acquisition system has traditionally included a Planx Pause AV and Pause Track for position, attitude, navigation information, plus Regal's RiAcquire sensor controller software. Now, more recently, the sensor is available with the TopalFlight flight management system. Specific improvements to the 1560 sensor platform has been the replacement of the laser subsystem with two new high-powered laser heads, capable of twice the output power of the earlier Mark II. This translates to a 1.4 times increase in range performance. In this chart, you can see that for the equivalent altitude, one can operate at twice the laser PRR with the Mark IIs versus the Mark II, significantly increasing point data density for the same fixed altitude. From a productivity perspective, the Mark IIs shows a potential 25% increase over the Mark II. These collection scenarios assume a corresponding scan rate that ensures an X equals Y point distribution, even at fast aircraft speeds at lower altitudes. With respect to data acquisition, there are really three primary steps. A definition of project specifications based on the application requirements and actionable data decisions to be made from the collected information. These include LiDAR point density, image GSD, data accuracy, coverage requirements, beam footprint maximums, and others. The second step is the translation of those specifications to sensor parameters in a supporting mission plan based on local terrain conditions, platform constraints, and sensor specifications. And of course, local environmental or weather conditions, and perhaps even local flight restrictions. And third, actual data collection that requires navigating the terrain and project area with the determined sensor parameters developed during the mission planning process. From a workflow perspective, translation of collection and deliverable requirements to actionable data involves the following software. The first is for mission planning, we use Regal's Reparameter software, followed by TopoFlight Mission Planner. And second, for actual data collection, we use RaiAcquire and TopoFlight Navigator. The focus for today's discussion is going to be on mission planning. Reparameter is a software that captures the sensor performance profiles in a convenient parameter-driven GUI interface. Sensor parameters are optimized based on the project requirements and the sensor profiles. These are then transferred to the TopoFlight Mission Planner software to create a flight profile. Here's a closer look at the Reparameter interface. It is divided into three sections that include project input parameters, sensor settings, and a visualization tab that plots what the corresponding point distribution might look like based on the parameters selected. The software also provides users the option to select different application types, such as wide area or even power line corridor, whereby the power line wire thickness can be specified to help model detection limits based on the sensor profile and the laser parameters selected. While not a definitive recommendation, it does help provide more realistic estimates of detection and required operating altitudes to help ensure collection success. Similarly, beam footprint size is included in this software for those projects that dictate maximum beam footprint over ground. TopoFlight consists of two software packages, Mission Planner and Navigator. Our focus today is on Mission Planner. And Klaus will now provide a live overview of the software and how a mission plan is created from project requirements, platform variables, terrain variation, and sensor definitions as they relate to the VQ1560 Mark II and the Mark IIS. Okay, Klaus, I'm going to pass the presentation over to you.
Thank you, Michael. Good afternoon, everybody. One of the nice things of our profession is that we are a small group. I need to show you my screen. Here it is. So we are a small group of people doing photogrammetry and laser scanning. So we probably know quite a lot of people, each other. So hello to everybody. As more and more disciplines are using LiDAR data, the requirements increase for the products we produce for the end customer. The more the end customer know what they want to get as a LiDAR or photo product, the more they exactly define their requirements, which have to meet. For this, we need not only good hardware, but also an efficient CAD-like software, which allows us creating flight plans. These flight plans need to be able to demonstrate that the flight plan meets the requirements of the project. We can't allow us to guess. We can't afford flying more than really what is needed as the minimum. And so here comes TopoFlight Mission Planner into play. Rufo Lomahan, my first customer in the US many years ago, told me that when he has to teach TopoFlight, he used to say that starting a TopoFlight project is similar to create a pizza. and and that's how it is. Sorry, I missed my here. So it's when creating a pizza, you need a dough first, and then you can create the ingredients. And similar is to do it with top of light. You have a basic data set, which corresponds to the pizza dough, and you need a project location. You need a digital Terra model because our reality is 3D and not 2D. And normally we have a map. We have a map as a reference to know how to know about the Terra. And finally, when we have this basic data set, we can flight plan. That's the pizza's ingredients. We have sensors which we select. We have the flight lines which we construct, and we have to make quality controls to show that our flight plan meets the requirements. And finally, of course, we need to calculate costs for our project. I start first with Reparameter. In our example, which I show, I selected 10 points per square meter as an example. And we have a speed of the aircraft about 170 to 200 knots. And when we calculate these parameters in Reparameter, we see those as results. What we want to, with these parameters, we want to create our flight plan. So we change to top of flight. Top of flight is here, and on the other side, as comparison, we see here Reparameter. First, we create our new project, and we define a location where we want to have it. It will be on my local disk, and I call it project one, and then I want to select the sensor. Of all those Regal sensors, I select here the newest one, 1562S, and I will come back to this. I just select that one. And next, I want to tell the software, where do we want to flight plan? For this, I have a project location. It is located in vector file. Here is my file of my location, and then I create this project. So this is my project location, and what I need is I want to see also a topographic map. If I have it on disk, I could use it. I don't have it, so I get it from Google Maps here. I start here the app for collecting Google Maps. And I want to have this area. Maybe this area here is what I need, somewhere here. And I do collect it. And you see it's collected it from the web, and it's grabbing picture by picture down and creates a mosaic of Google Map. Of course, if you have your own maps, you select it on your hard disk. In the meantime, when this map is being collected, I do import SRTM data, the digital Terra model. In my case, it is SRTM. And I get it from this area, and I download it, and I import it into top of flight. So we are still, in the meantime, here, the map has been collected from our area to flight plan. So I send it to top of flight. and we will see it will appear here. So it has been received. I didn't cover the whole area. It doesn't matter for this demonstration. And there, in the meantime, it's collecting the digital Terra model. Once we have collected it, it will stored together with our project, and we won't have to download it all the time, each time again. It will be part of our project. And that's now the last one. I can go back here. The map you select, you can also, like in Google Maps, you can select orthophotos, whatever you want, and bring it over into Top of Flight. And it will be a fixed stored as a file within Top of Flight. And it has finished, and I store it, DTM, I store it to my project, and I close it. Now we see, when you see it down on this bottom line here, you see the coordinates and you see the altitudes. I want to make my project area as transparent. The outline should be a bit thicker, a thicker line, and also orange colored. And we have here our area. Yes. Now let's talk about the sensor we want to use. I go back to reacquire, and I want to use those parameters I defined here. I want to use within Top of Flight now. I go and select again the sensor, and I check if I have already defined this sensor definition. In this case, I don't, so I add my sensor definition. I call it 10 points per square meters, and it will be available from now on. I select the camera I have. It's a phase 1 IXM 150. Where is it? IXM 150, 50 millimeter. This is the camera I have together with my scanner. It has a field of view of 56 degrees. For my flight plan, I will also set my scanner for flight planning only to 56 degrees. 56 degrees. The PRR I get from here. From here, I take all those parameters. This is twice 1850 is 3700. Yeah, it's too much, too high number, 3700. And the speed is 200 knots. 100 knots, and then we have altitude above ground. We fly 5,806 above the ground. And the scan rate is 452, and that's it. So we have defined our parameters, and it will be stored together with our project. We see here the minimum is 10.4, 12 a mean, and 13.3 as a maximum. The point distance will be 0.4 meters. And then I click OK, and I have my next definition, which I can use for other projects as well. So I select and close it, and we are now doing the toppings. We are just flight planning now. When we look at our terrain, we see we have a part is mountainous and another part is a flat terrain. So I want to make a plan, a part of my flight plan will be mountainous region, and the other part will be on the flat region. So what I do, I create an outline which separates my mountainous area from the flat area. I do this polygon. I can modify it, and well, for this demo, I think that's good enough. So this is my area. I see here it will cut my project area. So I do some editing. I will add something like this. Yeah, that's my one of the parts, and I collect another polygon, which is the area of the flat area, and so I do here this collection of this polygon, and this one goes along with that one. So this is more or less what I want to have. So okay, so we have two parts. I start with the mountainous part. I select this area here. I could select even my project area here. I could, but I want to select here my mountainous area as the active area, which is now yellow colored. I go and select my first flight line. It is, as we defined, as default above ground 5,807 feet. We want to round the altitude to the next 100 feet, for instance. We want to round the azimuth, and that's all. So we just draw a first flight line, and why does it run into Terra?
Klaus, I think your round height ratio is specified incorrectly.
Ah, that's it. Okay.
It's a big number.
Oh yeah, of course. Thank you. That's it. So that, of course, that's now it will. Thank you, Michael. We see here in our mountainous area, our coverage of the flight line depends, of course, of the terrain. We have more in the valleys, and we have less on the mountain top. Let us like it is, and let us the software fill the whole selected shape. This is my reference line, and you see underneath here, it's calculating the rest of the polygon. As it is very mountainous, it is a lot of calculation to be done in 3D, because to find the best altitude and distance between flight lines. So we have here the flight lines in red. In red color, we have the coverage of two neighboring flight lines, and in a gray color, we have the coverage of the single flight line. As next, we want to do another step, like doing a flight plan for this flight line. And here is, we see it is quite flat area, and we fill this area again with flight lines. Yeah, it's calculating. And these are the flight lines. And so we have our first flight plan. Now, of course, as a photogrammetrist, we see, or LiDAR flight planner, we want to edit some flight lines. I see, for instance, that this flight line here wouldn't be necessary. Let's say this can be deleted, and maybe that one can be deleted as well. We can edit, we can edit this flight line here, from here to somewhere here. And so whatever we want to, we can edit, add flight lines, or we can also add a flight line from here to here. So as a calibration flight line, And finally, we want to renumber our flight plan with starting at flight line number 1. And so there are our flight lines renumbered. And that's it. Maybe here we will add some here. I do it quite, as I have only a short time, it is quite a hurry here. So of course, when you watch the video, finally, we will show you, then you can see it in details how we do it.
That's a good point, Klaus. So for our audience, we've actually have a more detailed video for flight planning that Klaus has put together, and in the following week, when we send out the link to the webinar, we'll include a link to the more detailed video.
Exactly. So what we want to know is, now we have flight lines, but the question is, do we really meet the requirements of the project? And for this, we have a lot of tools to create quality maps. We need to, as a flight planner, we need to be sure that we get the point density per square meters. So we have a scale here, from 1 to 9.8 points a square meters. We will get red colors, and then yellow colors for this amount of point density. And so we see for each color a certain point density, which we can define, we can change, we can delete or change color, whatever we want, we can do. And then we will create a georeferenced raster map, in our case of 200 meters. We will, on the upper right side, we will create a legend, and then let's create our flight plan. Now, it is possible then, because we have here valleys, deep valleys, and it may happen that in certain areas we would not meet the requirements. We have here our legend, a big legend. Orange would be more than 25 points. We don't have this. The big area is between 11 and 15 points. And there are some, in the valleys here, we have 10 to 11 points. And we have here an area we can see which has less than 9.8 points. And then we can prove, is this acceptable for our project or isn't it acceptable? If not, I can, for instance, I can create a flight line here. I didn't want to do this. I delete it again. I wanted to create a flight line, let's say from here to here, and maybe a parallel line to the left. It shows you in the video, you will see it in details. And now we want to see what happened with our with our point density. So I can draw the map again. And now I see that we have filled these red colors, and we have again more than 10 points a square meters. So we need a software which allows us to quickly prove what if we get it. And of course, we have to show it to the customer as well, and that we prove the requirements. If we have large flight plans, we make always on the visible part the map. So if this would be our final map, I would color it again as point density map. And the next question could be, do we have enough rain? If we have here points per square meter, this is another layer now which has been created. And if we make it 40% translucent, so we can see the flight lines, we can be a colored map. So the next proof would be, for instance, the laser beam footprint. Can we what footprint do we have on the ground, and so we let it calculate, and the next map will be the laser beam footprint.
So that's kind of an interesting area where we're starting to get more demands for flight line planning or mission planning, whereby customers are saying we want beam footprint sizes no greater than X. So with the mission planning software, Klaus, you're able to define where those violations may occur.
Exactly, and I think it's important for the flight planner himself to be sure that the flight plan is correct, but also to the customer to that he knows the customer. We do the best before we go flying, and so we can explain the customer why we need some more flight lines, or why can we do it with less flight lines. So that's always an important part. Also for the customer.
So Klaus, actually, I just got a question from the audience. Someone's asked if we can pre-plan in, say, a terrain following mode, or are we constrained to a fixed altitude above the ground?
Yeah, if we have a helicopter, it would be nice. So we can do terrain following. So we would select this mode here, and the flight line would follow the terrain. Let us just create such a flight line to show you. I'm flying now over this mountain here, and we will see that we have quite a regular shape now. Of course, because it's from the left and right side, it's not a flat terrain, so we have a little distortions, variations, and so, but we are following the terrain now. So for those customers doing helicopter flights, they use this option of flight planning. So I go back to this, and now also there are a lot of quality controls. I will show them as a resume. For instance, the range. Do we have enough range distance? We have a nice flight plan, but what happens if the distance is too long? So we can prove it during the flight plan. So we have here, in this case, yellow colored are ranges between 2031 to 2600 meters. Of course, within the valleys, we have such ranges in the lower parts, and so that's always also the A safety. We can prove the A safety if we meet it, and we can prove it also for us, for the pilot, and for the customer. So these are important tools for flight planning. There are others like ground sample distance. We want to see what is the resolution of our imagery. So it's a bit more calculation. It takes a bit more time. So we can calculate the ground sample distance. If we do photogrammetry only, photo only, GSD calculation is a very important one. In LiDAR flight planning, it might be a secondary. It might be not so, normally it's not as important. So we soon will see it, the GSD map, and then we can see what GSD we have. Now, of course, I think time is running fast, so I need to export. Then the last thing I will show you interactively is calculating prices, so you can export the flight plan to Excel. Now it should appear, actually. Why doesn't it appear? It's calculating a lot. Here it is. I switch off the other maps, a range map, and I color GST, make it to 40% transparent, apply OK, and then I switch off the flight lines. And you see the GST values, dark green is below 12 centimeters, light green is 12 to 15 centimeters. So this is also a valuable information. And finally, if this is our final flight plan, we want to export it to Excel. We want to export it, and we can want to know what is the price for this flight we do. I can add my own Excel calculation grid. I have many prepared here. I think this one is the one I use now. It's now opening Excel, and we see here for each flight line the information, the speed, ground speed, field of view, PRR, scan rate, and number of images. We see the total of number of flight lines. We see the total number of triggers, images, the kilometers, the flight hours, 12 hours. And we have the minimum, maximum altitude. We have the amount of base phase 1 photo data. We know how that storage usage will be 33% filled. We need storage using of LiDAR data is much higher than we have in just on our specific selected storage data, and so we cannot do it in one flight, of course. And so these are all, and out of this data we can calculate the cost of the project. So creating a quote is always creating a flight plan, calculating the price, and then sending all this information to the customer. We can, of course, also export it in different file formats. The most used is Google Earth, of course. So we can see it directly in Google Earth, the flight plan. And so this is a visualization in Google Earth of our flight plan. Yeah. And I think time has finished for me to play around with this software. So I give back to Michael for some slides which we prepared.
So Klaus, thank you very much for showing me there. We have some questions that have come in, so we'll get to those at the end of the presentation. But following on from what you've shown us so far, you also had the chance to look at mission planning over the same area with both different sensor models of the 1560, the Mark II and the Mark IIS. And of course, in the presentation slides that I showed earlier, we have a theoretical performance improvement of about 25%. And so as we go through these slides showing the different output products that you described earlier, we'll get to a efficiency calculation based on the actual flight plans that you derived. So what does this first slide here show us?
On the left side, we see the 1562. For that same area, I just showed you how it works flight planning. On the right side, we have the 1562S, so just the flight plan. And we see on the right side, we have more spacing between the flight lines than we have on the left side. We see in the valley here on the left side, we have added some flight lines in the valley, and on the bottom here, on the ground here, because we needed to do a bit more flight lines because it is not as powerful, the 1562 against the 1562S. In the next slide, yeah. here we see the we compare 1562 again to S in ground sample distance, GSD, because we can fly higher with the 2S. We have not as the ground sample distance is bigger than it is in the 1562, because we are flying higher. So blue colored means 20 to 12 to more than 12 centimeters. And in the 1562, we have only a few areas with more than 12 centimeter GSD. In the next slide.
So in this case, Klaus, then if the client wants to maintain that same GSD, he needs to consider an alternative focal length for his camera. For example, if you'd selected 50 millimeters for these plans, then the assumption then is they would have to consider maybe a 70 millimeter lens now that they're flying higher for the same required point density and GSD.
Exactly, you're right. It's calculated with the same phase one camera, but you're right. So we had to consider a 70 millimeter camera, yeah.
Okay, now laser beam footprint.
Laser beam footprint is, of course, because we fly higher, the laser beam footprint is slightly bigger. Even we have a smaller laser beam, a narrower laser beam in the 2S model than we have in the 2, but the footprint, of course, is a little bit higher.
Now, from your experience, how often do projects start to dictate footprint size? I mean, clearly the larger footprint reduces the energy density, but that can be somewhat compensated with increases in laser output power. But what's the impact of beam footprint to the end user? Why does he care about that?
As far as I heard, there are some customers, they restrict the footprint to a certain size, but others, they don't care. They say, well, we have advantages, disadvantages. I think it is not that critical. As far as I heard from it's not as critical, the footprint size. Because the point density is more important for them.
Right. But I think in just to add to that, in combination with the beam footprint size, the larger it is, of course, there's a reduction in resolution, even though the density may be high. So it's probably a combination of the two.
Yeah, that's right.
Okay, and then these graphs compare the 2 and the 2S in terms of points per square meter from the laser itself.
Yeah, and we see that we have higher point densities with the 1562S than we have with the 1562. Yeah, we see
now, and this is despite the fact that we're flying higher. So we're flying higher, but we also have more point density even while flying higher.
Yeah, that's it. That's what we see clearly here.
Now, one of the questions that came in was when you start computing these different maps, beam footprint, point density, and whatnot, of course, it takes a fair bit of computing resources to do so. Has TopalFlight made any changes to the software to allow more computational processes to occur faster, such as say multi-threading, distributed tasks? What efficiencies have you incorporated or considering with the development of the software?
There are two things. One thing is multiprocessing is very difficult because it is making parallel processes would mean that we could create flight lines independent from each other. But the fact is in flight planning that one flight line depends on the other. And so parallel processing is almost impossible in flight planning, unfortunately. That's what we're thinking a lot on this. On the other hand, there are possibilities to improve the speed. One thing is to make it less accurate, so less iterations has to make, but this is not what we want to do. But there are also other computation, like computation with the graphic card and so on. Possibilities are there. And what we are doing in the background, what we are doing is we're creating a new top-of-flight software, and we will we started it in November of last year, and so we are bringing it out next year, not in 21, but in 22 we will bring the new top-of-flight software, which will be, of course, we will have improvements. And so we hope to make it a bit more efficient in calculation time. When you
Klaus,
have really, yes, please.
Oh, yeah, you described that to me earlier, and so we're looking at a brand new GUI interface. So it's going to be modernized. It'll have we'll have all the existing capability, of course, some new ones moving forward. Is that accurate?
Yeah, that's it. Mm-hmm.
Okay.
We have now many softwares out in the companies, and they have a lot of experience, and the software is now, when we started in 2003 with the first commercial software, 17 years of development, and that's always with software. Sometimes you have to start a new software when the old is still good and used, and so, but then from every 15 years, you have to think about creating the newest way of software technology.
Definitely. So based on your analysis, can you explain what you saw in the differences from a productivity perspective?
In this special project I showed you, we have compared 1562 again 1562S, and we have an increased productivity using 1562S of 33% of number of flight lines, and you see here less number of triggers, of course, because we have less number of flight lines. We have less kilometers flight line. Flight duration is around 26% less, and 39% less of photo data. So in this particular example I showed you, yeah, so it's obvious that 1562S is even more capable as the powerful 1562.
Excellent. In this slide, this is a productivity slide that we created, looking at the differences between the two sensor models, but looking specifically at Q1 versus QO2 collection scenarios. So, of course, the difference between 8 points versus 2 points per square meter. And from what we saw, we're getting the same or similar results as you've demonstrated here. So basically, in conclusion, you know, we've definitely seen a demonstrated increase in productivity from a mission planning perspective. We're looking forward to see the operational results of those with the first deliveries that are planned for this quarter. And and for our audience, I mentioned this earlier, we have provided a flight planning software capability in the past, POSTRACK, and many of our users are using that software. But now we also offer the TopoFlight package as an option for clients as well. And what Klaus has been demonstrating is it's fully connected to the Regal sensors. We've got compatibility with virtually all the sensors we have to date. The performance profiles are being built within the software. One of the questions that came up was the option for Reparameter to export information as a CSV file for entry into programs like TopoFlight Mission Planner. Klaus, maybe you can comment on that. How are we tightening the integration with respect to Reparameter into TopofFlight such that you don't have to manually enter those variables. Is that something that's been discussed?
Yes, yes. I should have done it since half a year or since a year. I promised it and I didn't fulfill this promise, but in the next release, you will definitively have it. It is quite simple. It would be quite simple, but it has to be done.
Nothing like putting you on the hot seat for that commitment, right?
Yeah, it is. Yeah. No, surely I have to do it. Yes.
Now you demonstrated clearly the integral camera planning, and in an earlier conversation, you had mentioned that you're in the process of integrating actually oblique image capture from a planning perspective as well.
Yes, this is now finished. This exists now. Oblique flight planning. It is not yet released. The testers are testing it, and I think it will be ready. I think it's good. It's okay, and so we will release it in short time. So I'll be finished.
Okay, great. And then, of course, you demonstrated to us the QA/QC map sets that you've been incorporating, the coverage, the density, the GSD, and then the more recent one are the range limits. And so one of the other questions an audience member was asking is, do you consider the full FOV in the range map, or are you just looking at the nadir distances?
No, the full field of view. Yeah.
Okay,
so
excellent. Yeah. All right, so that wraps up the formal webinar presentation. I'll take a look here to see if we've got any additional questions which haven't been answered. One of them is, for terrain following mode for flight plans, can you input a maximum aircraft climb or descent rate? Have you considered that, Klaus?
Yeah. This is also a question. This is also a discussed question. The response is no. It is just terrain following, and so we are discussing it, but it's not implemented.
Okay. Another question. Sometimes for safety and rugged terrain, it is necessary to plan a minimum height above the highest point of terrain. Is this planning method possible with TopofFlight? I saw only average terrain following mode and lowest terrain. So can we plan for the minimum or the maximum height, I guess, minimum to the aircraft?
This is correct. It is on the to-do list that we have to implement it. You're right. I think I have that's on my to-do list together with the Reparameter import, direct import. Yeah, you will get it, but not in this release now.
Understood. So I think we're getting to the end of our presentation. What we'll do is we'll capture the questions that haven't been answered, and we'll endeavor to get responses out to the audience. And I want to thank you, Klaus, very much for joining us today. The TopofFlight software has, I've heard so many good things about it. It's used globally. And it's a pleasure for us to start offering this capability as well to our clients moving forward. So for everyone, thank you very much for attending, and have a great day.